The first one is some frequency generation involving with a light wave and a microwave, which would be very inefficient. The second scheme is mixing the signal with two independent CW laser tones. Then you require demanding coherence between the two lasers. Okay? Well, I have a question. How demanding the mutual coherence is required if you want to take the second scheme? You have a signal spectrum, the first the CW laser, some frequency generation mixing. So the entire spectrum shifted to somewhere, right? Then the same signal spectrum, but the second CW laser mixing shifted to another position, and they are differed by 100 gigahertz, for example. So the frequency difference between the two CW lasers should be 100 gigahertz. Okay. And I mentioned you need demanding coherence. And how demanding is it required? Coherence is characterized by coherence time, for example. And do you know the definition of coherence time? The time period within which you have clear sinusoid, well-defined sinusoid. That is coherence time, right? How long the coherence time is required. The longer, the tougher, right? Demanding is just a qualitative description. Can you have quantitative description? 你随便拿两台 CW laser， 你要把它锁很稳，对不对 ？mutually 是 coherent， 维持多久才够？做这件事要维持多久 ？For example, 1 millisecond, 1 microsecond, or 1 second. Do you have some idea about the required coherence time in this implementation? Oh, I have to emphasize the required coherence time is not a constant. Universal constant is not. It depends on your measurement system. But depending on which parameter of your measurement system. What instruments do you need in performing spectral interferometry? You need an interferometer and delay, constant delay, and finally you need a spectrometer, right? To get the data. Okay? So the coherence time depends on which parameter in your entire system. Bandwidth. Coherence time 这件事不是有 okay. Usually when we talk about coherence time, we think about bandwidth. That's true. Okay, but this is not the case, not the specific case we are talking about. 我们可以再想想看有什么参数决定了你假设想用这个 scheme 的话 CW laser 所需要的 coherence time 是多长？我强调的不是单一雷射的 coherence time， 而是 mutual coherence。这两台频率稍微不一样的 CW laser 要彼此稳定哦，自己稳定不是我的重点，是彼此稳定多久？跟谁比？另外一个脉冲 ，if you compare with pulse width, it's usually very short, right? You are talking about femtosecond pulse. So coherence time, if it is about femtosecond, is easy. It's not demanding at all. Spectrometer 的什么参数？
就是上面反映那个时间后，在那个时间内，它是需要相改的，是吗？
Good. The data acquisition time. When you use a spectrometer, you can set how long the integration is performed, how long the shutter is on, right? If you set it's 10 milliseconds to capture one power spectrum, your mutual coherence has to be at least better than 10 milliseconds. If you choose 1 second, the mutual coherence at least has to be better than 1 second. The longer the integration time, the better signal-to-noise ratio, but the price is the mutual coherence is more demanding, more and more demanding. Okay, so it's a practical issue. And usually this is not the way we take to implement the idea. And finally, in addition to spectral shear big omega, a time delay tau is required in spectral interferometry. We need spectral shear as well as delay. Okay, we have to think about some way, not just to introduce spectral shear, but also mutual delay. So this is a very smart solution, the spider measurement. I used 2 slides to introduce the underlying method. So this is your signal pulse described in time domain and the frequency domain. The same signal, but represented in time and the frequency domain. And we assume the central frequency is omega 0 of your signal pulse. Then first you need a microsecond interferometer to create 2 pulse replicas with a fixed delay tau between them. Okay. Then you probably need a beam splitter to tap some power and pass it through a group delay dispersion line. And the purpose is to substantially stretch the signal pulse. So in the time domain, you will get a highly chirped, stretched pulse. And the different positions correspond to different local frequencies or colors, right? Then you can see the 2 pulse replicas see 2 local frequencies. The leading pulse sees omega 1. The lagging pulse sees omega 1 plus big omega. You see spectral shear big omega is created in this way, mixing with 2 different local frequencies. Okay. Then you can use a lens to focus the 2 beams inside the thin crystal for some frequency generation. And as introduced earlier, the 2 side beams are blocked by an iris. Only the central beam is passed. And this one will correspond to the product term between the 2 pulses, right? So actually, here we have 2 some frequency generation signals. First one is mixing between the leading pulse and the omega 1 frequency. Okay? So the spectrum is about the convolution between these 2 spectra. Okay? Can you tell why is that? Previously, we described SFG in the time domain. The central beam is about mutual product, right, in the time domain. But mutual product in the time domain means mutual convolution in the frequency domain, correct? So that's why you have convolution here. It's described in the frequency domain. And the first term means the leading pulse. The spectrum is centered at omega 0, carrier frequency. The second term means the local frequency omega 1 here inside the chirp pulse. So if it is a local CW frequency, you have a delta spectrum centered at omega 1. So that's why you have convolution between these two functions. It will be the SFG of the first SFG signal. How about the second SFG signal? The mixing between the lagging pulse and another local frequency. The lagging pulse is characterized by this function, a of omega minus omega 0 times e to the minus j omega tau. You see the spectral position is the same, centered at omega 0, but you have a delay, so you need a linear phase modulation in the frequency domain. And your local frequency is no longer omega 1, but omega 1 plus big omega, spectral shear. So the second delta function has to be modified accordingly. So this is the second SFG spectrum. Okay? But actually, SFG is a total field. So you have to sum these two spectra together. Okay? Coherent superposition. So in the time domain, the first leading pulse, after SFG, you got the frequency shifted pulse. The second pulse, also a frequency shifted pulse, but the shift amount are differ by spectral shear, big omega. Okay. And if we remove the common central frequency, omega 0 plus omega 1, you can write down the SFG spectral envelopes. Spectral envelopes does not count the carrier, right? So the first SFG signal spectral envelope is just A of omega. The second SFG spectral envelope is just A of omega minus big omega, the spectral shear, and the delay is taken into account by linear phase modulation. So you have this one and this one. After that, you use a spectrometer to capture the interferogram. So that means the interferogram is proportional to absolute square of the total SFG spectrum. Okay? And by substitution of the first and the second spectrum here, you got the formula. The green one is the background spectrum. The blue one is the magnitude of spectral product. And the red one is the central information, the spectral phase difference function between the two neighboring frequency components. Okay? So you see, setup like this can implement spectral interferometry, SI, with optical frequency mixing, and without the requirement of mutual coherence, right? Any question about SPIDER setup? Okay, so this slide summarizes how does SPIDER overcome the challenges we just mentioned. First, the spectral shear, big omega, comes from the difference between local optical frequencies. So big omega can be in the microwave regime, say 100 gigahertz, without actually mixing with microwave. All of them are optical waves, right? So the first challenge is overcome. Second, since the two local CW tones come from the input pulse itself, right? Where do the two local frequency, local CW frequencies come from? The chirped pulse, right? But where does the chirp pulse come from? The test pulse itself, right? 所以所有的东西都来自同样的一个 source， 叫做 test pulse。你只是把它分开，一路通过干涉仪，一路通过那个 dispersion delay line. That's it. So they share the common source. So mutual coherence is automatically guaranteed. Your interferogram can have stable fringes within the data acquisition time, for sure. OK， 所以两个很大的困难，在这个设计下都一次被解决了。So I said it's a very smart solution. Implementation of spectral interferometry to measure the spectral phase function. Okay. And you can also observe the delay tau and the spectral shear big omega are created simultaneously in this geometry. Okay. 两件事都做到，又有 delay， 又有 spectral shear， 而且它们是同时被制造出来的，不是分别用两个 system 去 implement， 一个 system 就 implement 出来。But there are some practical issues in SPIDER. First, delay and the spectral shear coupling. Okay, just like this picture. Microsync interferometer gives you signal pulse replicas. Group delay dispersion gives you a highly chirped pulse. And the mixing with two local frequencies give you the spectral shear, big omega. So you can see big omega and the tau are coupled with each other, right? They are not independent parameters. Okay. And then we know spectral shear is related to spectral resolution of this measurement, right? Because according to the formula, by the end of SPIDER measurement, you will get a spectral phase curve, but with discrete points, uniform. 每隔一个 big omega 你才解出一个点，对不对？所以这件事会跟我最后得到的解析度相关。好，然后这个图又告诉我 big omega depends on delay tau. You can say the larger the delay tau, the bigger the spectral shear, big omega, right? 如果 chirp pulse 不变，越大的 delay， 你的频率差就越大。这两件事是绑在一起的。然后很不幸的，我的 delay tau is related to average fringe density of your interferogram, as we discussed earlier. The bigger the delay, the denser the fringe density, right? And it's related to your spectrometer resolution requirement. And besides, delay tau also depends on input pulse width. Because delay tau has to be bigger than the single pulse duration, such that they are essentially separated with each other. 所以你发现好多事都绑在一起，对不对？我需要的频谱解析度跟我的 interferogram 的 fringe density 跟我的 input pulse width 全部都相关。OK， 那这件事是有缺点的 ，because your system needs to be recalibrated when measuring different pulses. OK, whenever your test pulse changes, such as the chirp rate changes, the bandwidth changes, you have to redesign the parameters. Tau, big omega, you have to redesign such that everything are appropriate. Okay, so basically, I would say SPIDER is a very delicate system. 很精密，很精致，但是也蛮脆弱的，牵一发动全身。The second issue, you need high-resolution spectrometer. This is easily understandable because our interferogram S of omega has dense fringes, the required spectral resolution, say the symbol is d omega, has to be tighter than the bandwidth delta omega. Okay, just like this figure, the blue dashed curve means the power spectrum of your signal pulse. And the black curve means the interferogram. To resolve the interferogram, you can imagine you need very fine spectral resolution, much better than the resolution required to resolve the blue spectrum, right? But originally, since the blue spectrum is your power spectrum, the resolution you require to resolve the spectral phase, the red curve, should be the same as, should be similar to delta omega. But since you intend to perform spider, resolving delta omega is insufficient anymore. You need much better resolution. OK， 知道我的意思吗？如果蓝色的是你的 power spectrum， 那这个是它的半高宽嘛？那你为了要把 spectral phase， 就是个红色的 curve 解析出来，你需要的解析度，合理来说大概就是1/几个 delta omega 就可以了。就是在这个半高宽里面 ，for example, you have 5 points, maybe it's good enough. So your required resolution should be delta omega over 5, for example. But if you want to resolve the dense fringes, delta omega over 5 is no longer sufficient. You need much better resolution. That's the idea. But if you look at the same problem in the time domain, it would be even clearer. After inverse Fourier transform, you got 3 components centered around minus tau, 0, and the plus tau, as we have known. And you have a finite window in the time domain, which is big T. Do you know how to determine big T? If the red function in the time domain comes from inverse Fourier transform of the spectral function, which parameter determines the time domain window? The resolution in the frequency domain, or d omega, right? 你在这个frequency domain 呢，相邻2个点有多少距离？取导数基本上就是这个 time domain 的 window size. That's according to the Fourier transform theory, right? So if you look at time domain, probably you would say the time window should be at least about 10 times of delta Tp. Delta Tp is the width here, the width of the P of t minus tau. 所以大概 window 是这个东西的10倍的话，这3个可以分得很清楚，而且都整个 window 里面。It's a rule of thumb. And this requirement eventually tells us the required spectral resolution in spider is about delta omega over 10. 大概就是这个半高宽的1/10，至少要这样才够。Okay, so basically you need a high resolution spectrometer to implement spider. And as I mentioned, the spectral resolution is a very expensive resource. If you order spectrometer with different resolutions, you will see the price will go nonlinearly. Right? 你要把你的 resolution push 个2倍 ，push 个5倍，那付的价钱绝对不是2倍、5倍啊，这是一个非线性函数，所以你要付出很大的代价，你才会有这么好的 resolution 去做 spider. That's the second issue.